Well, good morning, folks. Yes, I can now be a full-time astronomer since I retired from being a chemist. My talk this morning is about RS Ophiuchi, which is a star of which we only know 10 in our whole Milky Way galaxy, a recurrent nova. Well, what is a recurrent nova? It's a binary star system containing an elderly star. Let's see, does that work? I don't see the.
It has to be your mouse.
I don't see it. Oh, there it is. It contains a star that has gone through its evolutionary sequence and turned into a white dwarf, but is very closely orbited by a star going through the red giant phase of its existence. The stars are close enough so that the atmosphere of the red giant is within the Roche limit of the white dwarf. The stars are close enough that part of the mostly hydrogen atmosphere lost by the red giant falls upon the surface of the white dwarf and spreads out uniformly over the dwarf to form a very high pressure layer due to the 350,000 G surface gravity of the white dwarf. It spreads out over the whole white dwarf as a very thin layer. When the pressure and temperature at the bottom of the hydrogen layer becomes high enough, that's about 2 times 10 to the 13th atmospheres, and a temperature of 10 million degrees Kelvin, this will now sustain a nuclear fusion, and a thermonuclear explosion results in the sudden brightening of the system and the formation of a highly ionized plasma of hydrogen and helium and fusion products. The magnitude change is about from 11th magnitude to brighter than 5th magnitude for this particular nova. The normal continuum plus absorption line spectrum of a red giant with some nebular emission lines from the accretion disk of the white dwarf is replaced by a spectrum dominated by emission lines from the hydrogen and helium plasma from the thermonuclear outburst. This is a giant hydrogen bomb, is what it is. Here's a time lapse of what happened during the 2006 outburst of this nova, showing the expansion of the clouds of plasma from the explosion. That's from a paper by Bryant and Bode and Porcus, an asymmetric shock wave in the outburst of the recurrent nova. That was in Nature in 2006. And here's a picture by radio interferometer when the nova outburst was 13.8 days old, as well as the picture in the center there, which was K-band infrared taken from a telescope down in Chile. Now, classical novae, recurrent novae, and type 1 supernovae are all related. All three involve a binary system consisting of a white dwarf that is closely orbiting an aging red giant star with an extended atmosphere. A nova, an ordinary nova, of which we know many of in our galaxy, is the same kind of a system, but it's where where the gas stolen from the atmosphere of the red giant builds up on the surface of the white dwarf, and it triggers an explosion. For a brief time, the system can shine up to 1 million times brighter than normal. And as long as it continues to take gas from its companion star, the white dwarf can produce nova outbursts at regular intervals. A classical nova is most likely a recurrent nova that we've only seen erupt one time, and which has a long time between recurrent outbursts. A supernova is a violent stellar explosion that can shine as brightly as an entire galaxy of billions of normal stars. Astronomers divide supernovae into two types, type 1 and type 2. Type 1 is related to the nova I'm going to talk about, and this happens when the amount of matter in the white dwarf accumulates to the point that the mass exceeds the Chandrasekhar limit and the entire star blows up, just sending fragments out into the universe. These can be the brightest supernova and can be used to measure the distances to other galaxies. They're a very important standard candle these days. Type 2 are something else entirely, not related to the nova I'm going to be talking about. They're the final stage in the evolution of stars that are at least 8 times as massive as the Sun. Such stars reaches a point where it can no longer produce nuclear energy, and the core collapses, and the star becomes either a neutron star or a black hole. Different from the systems I'm going to talk about, which are all binary star systems. Now, there was an outburst of nova RS Ophiuchi in 2021. It had had 6 previous outbursts, starting in 1898 and going up to the most previous one in 2006. That actually occurred on August 8th, Sunday, the day the folks were leaving for home after the 2021 Stellafane condition. If it had happened the night before, most of the Stellafane attendees would have known about it. But it happened when we were leaving the convention. I first tried to have a look at it on the evening of August 12th. It was reported by the discoverer, Keith Geary, to be in the constellation Ophiuchi at these locations, RA 1750, 13.16 seconds, declination -6, 42 minutes, 28.5 seconds. Sort of in between these 2 stars, Nu and Mu. One of them is in Ophiuchi and the other is in Serpens, I believe. This is how it looks in my planetarium that I use at home. The nova is in the little teal-colored rectangle in the middle, and you see the star in Serpens and Ophiuchi. Zooming in further, you see that convenient little asterism to the left, and you follow the little curve around and you find the nova. Normally, it is extremely faint and difficult to see, but when I first looked at it on August 12th, it was the brightest thing in the field of view. Right there. This is what it would look like in the camera that I'm taking the images with. Now, I use 2 different slitless spectroscopy methods to observe the nova. And by the way, slitless spectroscopy is where the image of the object itself behaves as the slit for taking a spectrum. And I use 2 different methods. One of them, prismatic dispersion, using a detuned Schumann field mirror. Many people don't realize that the Schumann telescope is also a spectroscope. The other, I use a 100 line per millimeter grating before the sensor of a monochrome CMOS video camera. Well, for the spectra, the first spectrum I took with my Schumann in my observatory at home, this is the normal diagram of how you use a Schumann telescope. And I think I'm going to borrow the other laser pointer here. Yeah, there it goes. The Schumann telescope has a simple lens objective, a little field mirror back here, which forms an image of the objective onto the Mangan corrector mirror. There's the image sitting on top of it, and the curves are adjusted so that 2 passes through the Mangan mirror has exactly the same refractive power as the objective, only it's negative. So all refraction gets canceled out, including all of that bothersome chromatic aberration, which is why this is the perfect telescope. The image is finally formed off to the side after reflecting from a diagonal mirror where you have your camera or your eyepiece located. Now, normally, when you first look through a Schumann, if you're looking at a significant different place of the sky than you were looking the last time, you may find an image that's got little color fringes on it. However, you adjust the little knobs in the back of the telescope, and instantly you have a perfect color-free image. Well, what do you do to get spectra? Well, you leave the planetary camera or eyepiece in place, screw the yaw micrometer, that's the one on the top, about 4 turns counterclockwise, depending upon the threads you got in the micrometer screw, and the star turns into a spectrum. It gets spread out across the detector, and you have a spectrum that has spectral lines, either absorption or emission. Then you take the spectra. Shorter wavelengths get dispersed more in prismatic spectroscopy, and this particular telescope has optics by Jim Daly. They were sitting on a shelf gathering dust, so he sold them to me, and a wooden tube and all the little fiddly bits I made myself. Great telescope. It's my favorite telescope for observing the moon and the planets. I also use my C14 and a Star Analyser 100 grating from Shellyak to take most of the spectra. Here's a diagram of a Schmidt-Cassegrain telescope. This one has an f11 focus. It normally produces a more or less colorless image of the star. And if you put a grating in place, it disperses the image of the star into a spectrum with the longer wavelengths further dispersed than the short wavelengths, just backwards of the way a prism spectrum goes. You get the zero order spectrum, which turns out to be handy because you got something to measure from, and my grating is blazed for first order. Now what do you do? Well, in this case, I have been set up for live stacking of deep sky objects like galaxies and the like, and I had a focal reducer giving me f7 and a big sensor camera for getting galaxy pictures. Well, you take off that camera and you attach a grating to the nose piece of your camera, properly spaced to get enough dispersion, in this case 73 millimeters between the grating, which has the same threads as the filter, and the sensor of the camera. And then you insert the camera grating assembly into the same adapter that I used for the wide field camera for taking deep sky images. Take spectra. Now, here are the results I got using the Schumann. I first looked at the Schumann just to see if I could find it in the sky, and I was immediately impressed by the fact that it was quite red in color. It was one of the reddest stars I had ever seen. I then detuned the field mirror from its normal setting and introduced a spectrum. It was a faint continuum background with very bright emission feature at the red end of the spectrum and a somewhat fainter one at the blue end. There were other even fainter features present that I could see by eye. Now here is a picture I took of what came through the Schumann. Now you would expect to see color here, but this is a raw 8-bit video that I'm actually taking. And when it is processed, this is the colorful spectrum that you get. The bright spot on the left is hydrogen alpha, the same one that you see prominences on the sun with if you look through a solar telescope. And over on the right is hydrogen beta at 436 nanometers. And in between, there's a couple of helium lines and a few things that I don't know what are yet. Using the Star Analyser 100 with the C14, I got this particular spectrum with, again, but with the long wavelengths more further dispersed. And you can see hydrogen beta at 436, helium line, and hydrogen alpha at, I think, 656. And a few that I hadn't yet identified. Now there's a program that comes with the grating, if you buy your grating from Shellyak, called RSpec, and it's a very clever program. It digitally scans your spectrum and turns it into a map of intensity versus pixels along the length of your spectrum, and gives you some nifty features for calibrating your spectrum. I scanned the prismatic spectrum from the Schumann, and I used a second order fit to the hydrogen alpha line at 656 and the hydrogen beta at 486, and also the helium feature at 587.3 nanometers. You need 3 points on a prismatic spectrum because it's nonlinear. It's, the grating is linear, but the prism spectrum is not linear. I also calibrated the spectrum from the C14 using both the zero order spectrum at 0 nanometers and both hydrogen lines in the calibration. And this is the results from RSpec. The curved line on the left is from detuning the Schumann, and I've got a very nice fit to a parabola curve. And the one on the right is the linear fit that I got from the grating spectrum. You can then take these calibration curves and replot the spectra to get what's shown on this slide. The one on the left is from the Schumann. I didn't get quite as much resolution because there's really not as much, I could not get as much dispersion. I would have to tweak the image of the objective way off to the side of the image of the to the actual Mangan mirror, and I wouldn't have any light through the system. But on the right is the spectrum a few days later, taken with the C14 and the grating. Now, identification of the emission lines. By the way, normally when you see lines in the spectrum, they're in absorption, and they show up as either dark lines in the spectrum or peaks going down, negative peaks in the scan spectra. These are emission lines. They're not absorption. They're gases that are heated to luminosity and giving off the wavelengths that they would normally absorb in an absorption spectrum. Well, it was pretty easy to identify hydrogen alpha and hydrogen beta. These are part of the Balmer series of spectroscopic lines of hydrogen. And as well, you can see hydrogen gamma and hydrogen delta on the left there. I was also found information about helium online, and there's a number of lines in the helium spectrum which I was immediately able to identify on my spectrum. So, you know, if you take hydrogen and fuse it into helium in a hydrogen bomb, you're going to expect to see both hydrogen and helium lines in the plasma. Well, there they are. There's also some other lines from singly ionized oxygen, triply ionized oxygen. That's that nice blue line that the deep sky imagers like to use to in the Hubble palette to make those beautiful pictures. There's other possible lines, and down at the bottom I indicate some very highly ionized lines of iron
These are the coronal lines. We see those in the corona of the sun, and they're indicative of extremely high temperatures. Well, a few days of clouds later, I continued to take spectrum. This one is 16 days after the initial outburst. And you note that the helium line in the yellow part of the spectrum is considerably stronger compared to the hydrogen lines. I guess more fusion has been going on. Now, I wanted to estimate the magnitude of the nova, and what I did with this was I used my video finder. My video finder is a ZWO camera 174 MC that I had fitted with a 55 millimeter DSLR lens that I had set at f2.4. I took a 9-frame video of the star field around the nova using about a 4-second shutter speed and a gain of 285, and processed it in autostacker, keeping only the sharpest frames. I gave it a slight blur, and this was the image I obtained. Now, where is the nova? Do I get it? Yeah. The nova turns out to be that little star right there, and it's noticeably fainter than it was when I looked at it the first time in the Schuppmann. These are labels that I've applied, putting the magnitudes on the a chart that I got from my planetarium program. And if you look closely, you see the best match is to that 7.7 magnitude star over there. So 16 days after the initial outburst, where it was a little brighter than 5th magnitude, it's now down to 7.7 magnitude. I continued taking spectra and making magnitude estimates until the end of October, when I lost the nova in the evening twilight. I have 23 spectra and 16 magnitude estimates over that period of time. Now, here is the light curve of RS Ophiuchi during the 2006 outburst, data courtesy of AAVSO. And here is my curve, which you could just lay right on top of that. It followed almost exactly the same pattern in 2021 as it did in 2006. Now, the 2006 outburst was very well observed with magnitude estimates as well as spectra. There was the announcement in Sky and Telescope, Nova RS Ophiuchi just blew its top by Bob King. And the spectral evolution was followed by several people, including the group with Mondal and Annapurna that appeared in the monthly notices of the Royal Astronomical Society. They were using a spectroscope with a spectrograph with a slit in it, so their spectra are more highly resolved than mine, but I'm going to be using them to compare with comparable day after event explosions with what I took. What I found in general was that the pattern of spectral peaks was very similar to the 2006 outburst. The early phase spectra are dominated by hydrogen and helium, and the coronal and nebular lines appear in later phases at higher and higher intensities. Emission line widths are found to narrow with time, which is interpreted as a shock expanding into a red giant solar wind. I'm going to paste small scale spectra from that particular paper on top of mine to show how my results compare to the 2006 outburst. Well, here's my spectrum I obtained with the Schuppmann, 4.35 days after the emission, after the outburst, and here's my first grating spectrum, which was 7 days after the outburst. Overlaid on this, we have the 1.14 day spectrum from the 2006, and here's the 8.15 day spectrum superimposed on my 7-day spectrum. And you can see that the general features are very similar. The early spectrum is broader lines, and they claim that that one peak that I've called helium is sodium, and they have a very, very similar wavelength, that it might actually be both, with more sodium in the early stages. 16 days after the outburst, I got this particular spectrum, and here's the overlay from the comparable time of the 2006 outburst. 24 days. Now the ionized iron is beginning to show up. It's that hump on the side of the H alpha peak. 29 days. The iron peak is stronger. 30 days. 33 days. 37 days. You notice it's getting noisier because it's getting fainter. I'm getting less signal to noise ratio. And 49 days into the event, this was not a very good night. It was extremely noisy. But again, the peaks match rather well what happened in 2006. 50 days. And my last spectrum, before I lost it, is taken 72 days after the outburst. No, I got one at 84. Sorry about that. That's my last one. Here's an overlay of all of the spectra I got, and if you scan across it, you can see the changes in the spectrum that occurred over the course of this outburst. And here is the magnitude change with the spectra. I also tried to plot the ratios of the line maximum intensities relative to hydrogen beta, which was a fairly constant line in the spectra. And you can see that over the course of the outburst, the helium lines gradually increase in intensity. And the ionized oxygen lines, particularly the O3 at 5,007 angstroms, increases over the course of the outburst. And the iron lines, which are the highly ionized iron, the coronal lines, also increase over the course of the outburst. At this point, I'll take any questions you would have like. Yes, at the back.
How many of these systems did you say have you ever seen before?
How many recurrent novae? There are 10 of them in our galaxy. I think that some are known in other galaxies, but we only have 10. And there are probably more, but are hidden by the gas and dust. I'm sure they're going to show up with more infrared astronomy. But the curious thing is that not long after RS Ophiuchi popped its cork, U Scorpii did. That happened in June of this year. Unfortunately, I only managed to get one spectrum of that, and it was cloudy weather until the outburst was over. It was a very short period one. So kind of nifty that there's only 10 in the galaxy, and we got 2 of them popped their corks within within a year of each other. But there are probably a whole lot more that they just have longer periods, and we've only seen one outburst, so they're considered classical novae. They probably all repeat, though. Yes?
Is it usual that the iron would increase?
I think so. I think a lot of that iron is actually in the... Okay. Is it usual that the ionized iron lines increase over the course of the outburst? And I think it is usual, because those are thought to be actually in the atmosphere of the red giant, and that the shock wave from the eruption of the white dwarf is blasting its way into the atmosphere of the red giant and heating it up to temperatures that red giants don't normally have in their corona. So we can't resolve those. They're too close together to see, so we get the combined spectrum of both the red giant and the white dwarf and the nova emission itself. Yep. Yep. Yes?
So are these things predictable, and if not, is there any indication of when an outburst might happen?
The question is, are these things predictable? And the answer is yes, sorta. They seem to be, the 10 that are known, they are more or less periodical. I mean, you can't say, well, we know that this one's going to happen on August 21st, 2021, but they knew that one was due for that particular one. They just didn't know, you know, within a year or so of when it would happen. And this has been a fairly predictable one back into the 1800s. So it was 15 years. There have been 25-year gaps in this particular one. So yeah, they're periodic, but it just sort of depends upon how rapidly the red giant is losing its atmosphere and how quickly it's accumulating on the white dwarf. It's interesting that depending upon how massive the white dwarf is, it probably kicks off sooner for the more massive ones. And of course, they're building up mass slowly over the time. And eventually, they're all probably going to go boom as type 1As. So, yep. Yes?
Has there been any work on how these recurrent bursts change as the red giant loses more and more of its atmosphere? Or do they all kind of go the same way
As far as I know, they tend to go the same way, but it's kind of a sparse data situation. I mean, there's not that many of them, and we don't have, I think we've got more eruptions from RS Ophiuchi than any of the others. So it's a matter of accumulating enough data to make sense of it. But I think in general, they do tend to have an increase in the amount of helium over the course of the eruption and an increase in the amount of highly ionized species over the course of the eruption. So, yes?
Has anyone monitored the spectra of the star system over a long enough period to potentially use the spectra to predict more precisely when an event might happen? Like if it's roughly 15 years between events, has anybody monitored the spectra over the course of 15 years
Right.
to see if there's a noticeable change leading up to that?
Well, I know the AAVSO members monitor the magnitude of the things in between eruptions. I don't know of anybody taking spectra in between the eruptions. They get pretty faint, and it may be out of the reach of most members of AAVSO to do that, but it seems like a good thing to do, yeah. So, yeah, in fact, I got to talk to the ASVSO people, see if they want my data. So. You do? Okay, talk with you about it later. Any other questions?
Peter Bielo later, he's promoting the AAVSO this afternoon.
Okay.
And were you at the Hartness House workshop on Thursday?
No, I wasn't.
Because one of the talks there was on recurrent novae and exactly what you're talking about.
Oh, wait, Hartman's house. Yeah, I was there. I heard
Yeah.
that specter, and I've been talking with Joe about that since then.
Yeah.
So yeah. Now I'm a member of AAVSO, but I have not been an active contributor of eyeballed magnitude estimates. But maybe I should start doing that. Yep. So. Oh yes, Eileen.
The giant red star ever finally gets so depleted of its material that it
Well, it's got to, but this is such a long time scale, and there's so few of them that we've never seen one go supernova yet while it had the white dwarf around it. It's got to happen. And if it's a smaller star like the sun, undoubtedly what's going to happen is you're going to get one of those beautiful bipolar planetary nebulae because it'll be modulated by the rotating white dwarf going around. Well, so who goes around who there? Depends on how big the red star is. But usually the white dwarf was a bigger star in the first place, and that's how it got to be a white dwarf first. So it probably went through a phase with a planetary nebula a few million years ago, and eventually the other one will too. But I don't think anybody has observed a known nova or
particularly recurrent nova, with the secondary star losing its atmosphere. Yeah. Well, I think that's about all the questions.